Listo, profesor Isaías.
Thank you. Uh, Thank you, everybody. Good morning, everybody. Today I'm very pleased to introduce Professor Alexander Kordyuk from Kyiv Academic University. He'll talk for us about band structure analysis of the band structures. I know I knew Professor Alexander 2 decades ago in Bariloche in the school of the ICTP. In this school, another Alexander was participating, Alexander from Cuba. Well, Sasha, you have 1 hour to talk for us, and after we have a section of questions. With you, go ahead.
Okay, thank you, Isaiah. Actually, I prefer if you have questions, just interrupt me whenever you want. So usually, and of course we can discuss some questions after the talk. So thank you for this invitation. Sorry for the previous time that I understood that it was the time shift and change with this from summertime to winter time, and that was unfortunate. Sorry for that. Actually, I want to talk about my research and what I'm doing about also organization, project, and so on. When we met Isaiah long ago, and that was in previous century, right? My interest was about flux motion in superconductors, magnetic flux dynamics, vortices, and so on. After that, I switched to more fundamental investigations. I'm an experimental physicist, but I'm completely switched my technique to photoemission spectroscopy, which is dealing with electronic structure of solids. Therefore, here you see this images of levitation, which I did before, and I actually studied how such levitation system, how with this levitation system you can construct very precise experiment to investigate the magnetic flux dynamics in superconductors, some peculiarities of this dynamics. But on the big scale, of course, it's most interesting for me is understanding of mechanism of superconductivity, and this is about, as I learned later, it's about understanding of their electronic structure. Therefore, one moment. Okay. Therefore, today I will cover and some my experience and new results. And speaking about my affiliation, so now I'm a director of Kyiv Academic University, and I spent essential amount of time for organizing or for inviting, appealing some young people, students to physics. It is the main aim. But also I have a number of other affiliations, and I'm a head of Department of Superconductivity at the Institute of Metal Physics. We now collaborate with Leibniz Institute for Solid State and Material Research in Dresden, where I spent, I think, about 10 years, but now we have a common project, which is called the German-Ukrainian Center for Quantum Materials, which is for building in Ukraine the German-Ukrainian Center. It is funded by BMBF, the German Ministry of Education and Science. Also, I'm very interested now in the development of which we called it now Light for Ukraine project to build in Ukraine the synchrotron. And as the first step, we consider it as building of Ukrainian beamline at Solaris synchrotron in Poland, in Krakow. And a few words about my main affiliation, my work. about Kyiv Academic University. It is a special university in a sense that some time long ago I could say that I also studied there because it was summer form. We studied 4 years in Moscow Institute of Physics and Technology, and then moved for 2 years to Ukraine, and worked here already in research institutions. And this form, or this is research education. We are now developing and further, and especially it is important to combine it with international collaboration, because nowadays research, of course, the idea is simple, that students learn much more effectively if they involved in real research. But motivation, of course, depends on how this research is interesting, how it is for a front research, start of the art. And this, of course, impossible now without close international collaboration. Therefore, it is also the prime direction of the development of our efforts. So we are developing this education with and also to be interested, we developing some interesting research directions. And these directions now it is, of course, artificial intelligence and quantum materials and quantum technologies. And I will speak about later. So actually, the main idea about in my presentation is that electronic structure of solids is a key for understanding of the properties of the material, for design of new materials with some functional properties, which we call now theory-assisted search for new quantum materials. And of course, I will explain some examples as high-temperature superconductivity and details about this electronic structure. And it is important now the search for topological superconductivity and the development of electronic elements for quantum technology, like for quantum computing. So this 4 panels represents the way of from materials and their macroscopic properties to electronic structure. But to measure this electronic structure, you need synchrotron experiments, and it is also interesting how to combine it and finally to make some devices based on this knowledge. So this is approximately the plan. Quantum materials. You of course know that quantum materials is quite new, comparably new trend in naming, because from physical point of view, all the materials are quantum, of course, because all of them, to describe all of them, you need understanding of quantum mechanics. But this notion about quantum materials, it's appeared not long ago, and now many groups appear in studying of quantum materials, and they are related somehow with second quantum revolution, which is related to appearance of such quantum technology as quantum computing, quantum communication, quantum sensing. But to somehow formulate which materials could be called quantum materials. Actually, you could refer to these papers which explain it especially. But people introduce some notion as emergence. So some phenomena, it is called emergent phenomena. So if in material, to understand this material, you have some properties which in a whole, in interaction, appear some new property. And this is, of course, in general, it is termed to get together under some one umbrella some interesting materials for technologies like superconductors, strongly correlated materials, electron density systems, charge density wave, spin density wave, topological materials. Here also goes ultra cold atoms, cold excitations, but I will focus first on the on superconductors, not first, but mainly on superconductors. And superconductors, they are the most, let's say, trivial or old example of quantum materials, because it is really technologically, you could find it in many places, starting from this large scale, largest scale experiments like Large Hadron Collider or ITER, International nuclear reactor, thermonuclear reactor, yes. And this is in construction of magnetic resonance tomographs for everyday use in medicine, and for superconducting quantum computers, for example. And superconductivity, the history of superconductivity started long ago by Cameron Konitz, when he managed to obtain, to liquefy helium. And with liquid helium, it was possible to make low temperature experiments, precise low temperature experiments. And the first thing which he found, it is superconductivity in mercury. And this, let's say, old types of superconductivity, it's appeared that it's hard to find materials which is that does not go to superconductivity at sufficiently low temperature, or maybe at some pressure, something else. And the properties, the model for this phenomena was introduced in 1957 by so-called BCS theory, Bardeen-Kapper-Schrieffer. They suggested that electrons pair with exchange of phonons, with exchange of some vibrations of the lattice. This model mechanism explain superconducting gap and explain many things which was observed, but it was accepted. I wanted to say that it is immediately accepted, but not. I found that actually Nobel Prize was awarded not very fast after discovery. My impression before was it was just a few years passed, but it took some time in fact. But comparing to high temperature superconductivity, it was probably fast. And the main so-called smoking gun experiment, which with which people, all researchers believed that it is the true mechanism, that was so-called fingerprint experiment. Then in tunnel in spectra, if you measure current voltage characteristic for the tunnel junction between metal and superconductor, you have something like this. And if you differentiate it, you have something like this, which represents the density of states. And in this density of states in superconductors, they are perfect objects to apply this technique, because they have very fast changes of the density of state due to opening of the gap. And but what is more interesting than here, that everything in this electronic structure became shifted by this gap. And here, if you differentiate it even more, and you can get some thin structure, and then thin structure here is hidden all the interactions, all the important interactions which form superconductivity. And that time it was shown that these peaks here, they are identical to the positions, energy positions of the optical modes of phonon modes. It is that therefore this interaction was caused by phonon spectrum. Therefore, it was evidence that it is phonons. That Bardeen-Kapper-Schrieffer are correct. That it is phonons which are glue to explain this superconductivity. And when in already also long ago in 1986, high temperature superconductors, cuprate superconductors have been discovered. People believed that very soon all cities will become superconducting because superconducting applications were foreseen very real. But with time, this kind of superconductors, they appeared much more complicated. In a sense, not maybe the electronic structure, but their properties, and especially due to strong correlations. And now we could say that it is still many years, past many years, we do not have theory about high temperature superconductor, which says what to do to increase critical temperature. We have many theories, and it is also could be a problem that many theoreticians suggested some theories which they like, and they prefer that their theory win. But to be honest, no theory could help to predict new superconductors. And also, I could say that there is maybe no such a smoking gun experiment which shows which theory is correct. At least there is no widely accepted experiment. At least one of our experiments is like this experiment, but it of course has some difficulties to be accepted maybe. And the problem with why not to do the same with high temperature superconductor, just to do similar experiments, tunneling spectra and looking for fingerprint. And this is because this superconductor shown that superconducting gap is not uniform around the Fermi surface, or it is not uniform in space, let's say, in reciprocal space, because it has some symmetry which is called D-wave symmetry, and this means that at some portion of the Fermi surface it is maximal, at some portion it goes to zero. Therefore, when you integrate everything in tunneling experiment, you have some integration, and you have all these features, spectra of interaction shifted in different amounts. Therefore, all the picture is smeared out, and it is difficult to extract any information. And to do it, you need to compare already angle momentum result. You need to have momentum result electronic structure and compare it with momentum result structure of the excitation spectrum, with spectrum of phonons or other spectrum. And it is appeared for my point of view, and many people agree with this, but there are still some people who believe in phonons in high temperature superconductors. But most real, most probable it is that this glue between electrons is made by exchange of spin fluctuations. So instead of phonons, you have spin fluctuations, and from such a comparison of electronic band structure with the structure of spin fluctuations, you see that they are consistent in a sense. I will now explain what is this electronic structure, because I started just to speak about it, but I understand that I need to explain it. So what is electronic structure? Actually, photoemission experiment, which it is my favorite now method, it measures just the photoelectric effect, based on photoelectric effect. If you have photons with certain energy, you shine them to sample and you excite electrons, and you apply the energy conservation law, that if you know the energy of photon, it absorbs, and you have actually photoelectron. You can measure its kinetic energy, and it is also it goes, the difference of energy of photon and kinetic energy of electrons is a so-called work function, but it is also the binding energy of electron in solid. So, and if you measure with these photons, you measure such a spectrum, And by this spectrum, such a peak you see in this spectrum, and this peak represents this different binding energy for electron from different orbitals, right? But it is more interesting that near the edge of the spectra, it is called Fermi age, the maximal energy which you get, maximal energy of electron which populates this solid. You have much more complicated spectra, and this is called valence band. It is not so single peaks because they interact with each other. Many atoms in solid interact, and the spectra became widening. But it is more important that if you can resolve not only energy but also momentum or angle at which electron escapes solid, then you have something like this, and this is electronic band structure. People long ago have managed to calculate the electronic band structure and to understand it in terms of solving of Schrödinger equations for electrons in periodic potential. But that it is a real thing, it is not theoretical concept, became clear only when angle resolved photoemission spectroscopy appeared. And it is a simple experiment to understand because you have a sample. It should be a single crystal sample because, of course, to have this structure, right? Not integrated over all directions. And when electron absorb photon and escapes, you have here electronic lens which just make all electrons which escape at one angle, it makes them projected to the entrance slit in one point. So for this, you should be in focus for this electron lens. Sample should be in focus, right? And therefore, you have here resolution in angle. And with hemispherical analyzer, you do not see here the upper sphere. With hemispherical analyzer, so here is electrical field, right, in between these hemispheres, and you have a resolution in energy, therefore. And here at the channel plate, finally at the channel plate, you have the distribution in angle and in energy. And angle, due to momentum conservation law, you can easily calculate into momentum of the electron which it has in solid. Therefore, with just in this image, you have already distribution of electron, how it was in solid, which it has energy and which it has momentum. And it looks like this. In fact, it is also called, I call it now electronic structure because, and it is called electronic excitation spectrum. And it is also okay, it is also so-called spectral function, but I will explain what is this in a bit more details. In a sense that this is clear representation of the quantum mechanics if you measure the spectra, experimentalists measure the spectra and understand how it looks like. So it is everyday experience when you see a manifestation of the quantum mechanics. And this manifestation, what we see here, we see, even if we consider electrons like classical particles, their relation of their energy, kinetic energy and momentum is p squared by 2m. And this is parabolic, so-called parabolic dispersion. But it is important that we have two principles from quantum mechanics. We have Heisenberg uncertainty principle and we have Pauli principle. And from Pauli principle, that means that electrons could live only in one state. You could not put in one state more than one electron. And these states, they are defined by uncertainty principle. It is the size of the state or distance of the state. If you know that electrons are in some sample of the size L, this means that you know its momentum with some uncertainty. And this is actually the minimum size of this state which you could pack here. And therefore, if you have along this parabola, free electron parabola, you have a number of states, these points, where you could put actually two electrons with different spin.
Alexander,
Yes.
we have a question. Leandro, can you do your question? Just a moment, Alexander.
Yes.
For sure.
Yes. Alexander, thanks very much for the very nice introduction. I just when you were presenting, I had a question about the previous slide about the intensity. So yeah, the previous one before. When you were yes,
This?
here. Yes,
Okay.
yes. So you presented the I understand perfectly the condition of where do you find the signal. So the different yes. So how the spectrum is reconstructed. But my question was about the information in the intensity. Just that. Thank you.
Yeah, of course, it's a very interesting question in the sense that, of course, the position of the band is calculated by band structure calculations. Intensity, it is a bit different thing. First, intensity, it consists of so-called matrix elements. So it is, for me, a golden rule, so-called, that describes of the probability to excite electron to some state, the probability to absorb photon and to excite electron. And this probability, it is depends on interaction of this electron, the electron of in this state with photon of different polarization, energy, so on, but also from the place, for the free space, free place in this reciprocal space. So that density of state in the final state should be also possible density of state should be there. And this is one important thing. It is actually the main important thing. In this sense, I show here it is occupied electrons, and there above them there are many other bands. And if electron with some energy can absorb some energy and find above some free state, unoccupied state, then the process is more, you have more intensity then. But also it is interesting. I will show a bit later how intensity is distributed over different brilliant zone. Because if we speak about electrons, we speak about Bloch waves, not the plane waves. And the electrons which we catch in analyzer, it is already plane waves. So you have some projection of the Bloch state to the state of the plane waves, and this is also contributes.
Thanks very much. Very clear.
Okay, so I continue then, so it is important that electrons here, which number of electrons which you have, with them you just populate this available states, and when you finish with electrons, the maximal energy is so-called Fermi energy, and the maximal momentum is called Fermi momentum. And this actually 2 points, yellow point, actually the edge between the boundary between occupied and non-occupied state and unoccupied states in the reciprocal space. The reciprocal space I call the space of momenta. It is the Fermi surface. And if you, the Fermi surface is because we live in 3 dimensions. Now I just spoke about one-dimensional case, and in one-dimensional case it was free electron parabola, and these 2 points are represented Fermi surface. But in 2-dimensional space you have already such a paraboloid, right? And the Fermi surface is the circle. And in 3-dimensional, just the Fermi surface will be sphere, and to imagine electronic structure, it is more difficult, because you see, for electronic structure we need extra 1 dimension. It is energy, and therefore you just could try to imagine, or just to projection, to imagine projection. So But on the other hand, it is not maybe so important because most interesting materials, they are quasi two-dimensional. And it is also, there is a reason about it, but it's not the topic of my talk now. And if we speak about Fermi surfaces, of course, even in simple materials, it is only for the materials of first group. It looks like spheres, and for all other materials, it is more complicated. Fermi surfaces, they have several sheets, and not to say about much more complicated materials. And going back to this spectra to explain about a bit more what we have here more, it is not, you see that the intensity, it is not just like points or one line, it is some distribution of the intensity. And this distribution, it is not just due to experimental resolution or something, it is just due to physics. It is due to interaction. Interaction smear it out. And this, to understand it, we should switch from idea of free electrons, or almost free electron, to idea of interacting electrons and to idea of quasi-particles, in a sense that quasi-particle, it means that it is electronic one-electron excitation that have some certain time of lifetime and probability to decay. And they described by self-energy, and actually the width of this distribution is proportional to this self-energy. And self-energy, imaginary part of self-energy, it is probability to scatter for this quasi-particle. And real part of self-energy, it is some shift in energy, renormalization of this dispersion. So important point here is that from what we see here everything. We see, and the skeleton for this is the bare dispersion of the non-interacting electrons, but real electrons are smear out about it, but you can extract this information about interaction also from this electronic band. And I now did not tell nothing about actually interacting with potential. This is, of course, would take much more time, but briefly to say that if we have not just a uniform sample, but we have crystal structure, periodic crystal structure, and periodic potential, then instead of this free electron parabola, you have this parabola shifted. You have just like a Fourier transformation of this interaction. And this is called Bloch electrons. And this means that instead of one parabola, you have a number of bands, and you have new scale in the reciprocal space, which is called Brillouin zone size, or reciprocal vector. And this vector is inversely proportional to the difference, to the distance between atoms in atomic lattice. Therefore, this is actually, this shows real distribution of the electrons. This is experimental data. And you see these bands, there are many bands. And why it's moving? Because it is just plain representation. This movie represents just three-dimensional space where you have kx and ky, and in vertical you have energy. And here is the Fermi level, and this distribution of the electrons. From this distribution, you can understand an interaction of electron with crystal lattice in terms of band gap, band width, and in terms of actually harmonics of you could understand all this interaction. And with this smearing out, you could get information about interaction, important interaction. And actually, we need to compare it also with calculation to understand which band is where. And we need quite long range of parameters. So to measure the whole valence band, you should have about 5 electron volts in depth. But to resolve fine structure like a superconducting gap and some interaction consequences, you need resolution up to milli-electron volts. The same is for momentum space. And I see that I will skip some information to say that also very important the properties of the photons. And in particular, it is important to have, it is exactly about your previous question, that intensity distributed differently, and when you change the energy of the photon or polarization of the photon, you change this matrix element first, and you could shine different light on different bands, and therefore changing possibility to change the photon energy give you like a color vision compared to black and white vision. Therefore, it is the first reason why synchrotron experiment is important. And a few words about synchrotron experiment, because actually my first experiments were made in Dresden in laboratory, and light source was helium lamp with only one possible energy. But when we came with our system to synchrotron, we understood that it's much better. And synchrotron light, it means that you have some beamline from synchrotron, and you can, it is very bright compared to other sources, and you could change and excitation energy and polarization very freely. But for this, of course, in this experiment, you should be in UHV vacuum, because it is very surface sensitive. This is just looks like in experimental chamber. Just I will show a few photo how this vacuum chamber looks like. It is quite big apparatus finally, because to make everything in high vacuum, it is difficult. It is how typical synchrotron, it is BESI at Berlin synchrotron looks like. The synchrotron which I also like, it is so-called Swiss light source in Switzerland. There are some synchrotron which I attended, and in the world now we have more than 50 synchrotrons which are very important for research. So I will speed up. The main conclusion from my experience, experimental experience, it is about importance of electronic band structure. From one point of view, it is trivial conclusion, but on other case, not all people believe in it, because still. But my evolution of my understanding was from this demonstration of the importance of spin fluctuations in cuprates to iron-based superconductors, and then back to cuprates, to understanding that actually electronic ordering should play also a crucial role. And a few words I would also say about how this electronic band structure is important to make a new electronic devices. So this is electronic structure for cuprates. I just briefly show again, and I have shown this slide without introduction, but now after introduction, I should say that having electronic band structure, you could calculate electron susceptibility. Electron susceptibility, that means that probability of electrons from here go to here interacting with other electrons. And this is actually, when they exchange with spin, this is actually how you could, from electronic band structure, calculate spin excitation spectra. And therefore, actually, you could just use electronic band structure, calculate spin fluctuation spectra, and to see that it is this spin fluctuation spectra, then pair electrons. And this is important thing. And this spin fluctuation spectra, it was observed in neutron experiments, and it is separate interesting story. But it is also interesting that this electronic structure, when you have this electronic structure, it is already tells you how stable is this electronic system, how it is stable, or it is better for it to form new ordering, some superstructure. And it is interesting example, the transition metal decalcogenides, and with variety of charge density wave transitions, and this is called Pierce transition. And here I just wanted to say that analyzing electronic structure, we have seen that from it we could predict how it will behave, whether it forms some additional ordering or not, and when this ordering forms, you see that some band gap is opening. Band gap is similar to superconducting gap, but it is opens when this crossing of the bands appears, right? Or at the always at the boundary of the brilliant zone. Okay, I see that time goes on. I will skip it. And I more want to say about to speak about iron-based superconductor, because what I said about that there is no theory to predict how to say what we should do to increase critical temperature. It was discovery in 2008, iron-based superconductor, complete superconductors, completely new family of superconductors based not on copper but on iron, which is believed should not be superconducting due to magnetic moments, but anyway it is superconducting. They are similar to cuprates, that there are many different compounds, and they have also this complicated phase diagram when temperature, you see in the diagram, in the plot of temperature versus concentration, electronic concentration, charge carrier concentration, you see the different phases, and you have superconducting phase, not for stoichiometric case usually, and you have some magnetic phase. In cuprates, this is antiferromagnetic phase, but not insulator. Here it is antiferromagnetic, but metal. And there is some ordering, and this ordering, it was also similar. But comparing to cuprates, it has much more complicated band structure. Instead of one band or two band in two-layer cuprates, it has 5 bands, and actually 5 Fermi surfaces. They looks like this. It was how predicted, and that was our first paper about it, when we shown that it is not like this but like this. Then we believe that it is the consequence of ordering, magnetic ordering, but later we have found that it is not. It is really such electronic structure. It is just shifted sufficiently, essentially shifted comparing to band structure calculation, but nevertheless it is electronic structure by these compounds. But what is interesting about this compound, important about this compound, that they are like a Lego constructor, that you have similar bands. You have always these 5 bands, but in slightly different position for different compounds, for different doping. With doping you could shift it, with pressure you could shift it, and you could find empirical relation between electronic band structure and superconductivity. And we have found that it is very important that maximal of TC appeared. You observe maximum TC when the top of the bottom of some bands, important bands, goes to Fermi level. From point of view Fermi surface, that means that Fermi surface, it is when electronic structure crossed by this Fermi level, and it is then Fermi surface. And Fermi surface in 2 dimensions, we have small Fermi surface. When it crosses here, it is this Fermi surface, crosses here, it is this Fermi surface, and you observe the maximal of TC then. Still, there is no theory to explain it completely, but there is some ideas that this small Fermi surfaces worked such amplifier of superconductivity in larger Fermi surfaces. This is also different story, but when we go back to cuprates, I should admit that that model which we suggested about spin fluctuations, that may be not complete, because here is difficult to calculate theoretically, because so-called vertex correction due to strong interaction, and you should anyway introduce some parameters by hand. You could not make it from first principle calculations. But and therefore you could, based on the same structure, you could predict quite critical temperature in quite a range. But it seems that in cuprates the situation is similar, and if we consider, and it is in fact it is not cuprates, it is back to cuprates here. So This is so-called phase diagram of the cuprates, right? And here we have antiferromagnetically ordered phase anyway. And here we see this ordering. It appears like I shown you for decalcogenides. But here we usually do not see it. It is so-called pseudo-gap region, but it does not mean that there is no here this ordering. It should be here, and it seems it here, but it is just it is smeared out in reciprocal space. Taking it into account, we could say that situation is expect that situation in cuprates is also similar, that we need to understand this mechanism of enhancement of superconductivity with these small Fermi surfaces. But this work is still not finished. And finally, I wanted to illustrate how the knowledge of electronic band structure is important for making new devices, and in particular for superconducting qubits, maybe for superconducting computers. And you know that superconducting computers, it considered very perspective in a sense that all companies now work on their version of superconducting computers, and the question how many qubits you could correlate, you could entangle how many qubits, and the main problem here is the coherence, because even at very low temperature, at millikelvin, when this qubit operates, thermal fluctuation ruins this entanglement. And in order for quantum computing to work, you need at least several thousand, 10,000 or 100,000 of qubit correlated. And at the moment, it is just a few hundreds, right? It seems that a serious obstacle. I think evidently the problem is small superconducting gap. And small superconducting gap, the superconducting gap here, it is proportional to superconducting temperature, and the technology here is well elaborated, aluminum technology. It is good in a sense that it gives you very reproducible result, because aluminum is easily covered by predictable layer of aluminum oxide. And it is insulator, and it is easy to make a Josephson junction, a tunneling junction, let's say, with superconductor, but between two superconductors. This TC define the superconducting gap, and for this gap, this frequency at which qubits communicate to each other is in microwave range. And it is comparable to this low temperatures. And one of the solutions is to increase the superconducting gap to switch to another superconductors. It is, of course, there is technological issue, but it appears that it is also a principal issue, physical issue, because we could do it. In aluminum, the gap is 0.3 millielectron volts. And in cuprates, it could be 2 orders of magnitude higher. And of course, it would be very appealing. And one of our interesting results was to try. We were the first in the world who succeeded to make good Josephson junction between iron-based superconductor and traditional superconductor, in this case, niobium. But and I expected that this experiment will prove that iron-based superconductors have no this sign change of superconducting order parameter as it is believed. But this experiment disproved this my idea, because we see that this is a ratio IC/Rn, which should be proportional to superconducting gap, was much more smaller than it would be expected for isotropic superconductor. It is because destructive decoherence, when you have some transition from plus to minus and from plus to plus, therefore you have phase shift, and they almost similar, and they almost kill each other. And this is actually for all high high temperature superconductors, also for cuprates. So you remember I told it is D-wave symmetry. It is also sign changing symmetry, and it is also for iron-based superconductor. But then we have found interesting thing that if we put a thin layer of copper in between niobium and iron-based superconductor, this value increases 40 times. And 40 times increase, it was unbelievable in a sense that we expected just copper, which is not superconductor, it will reduce this value, but it is increased, and we understood why it is. Because the Fermi surface of copper, which is integrated, it is simple, but it is when it integrated, it looks like circle. And this Fermi surface just looks like a filter in reciprocal space. Just because when we have electron which goes from niobium, which is distributed and it goes to iron-based superconductor Fermi surface, and it goes through copper Fermi surface, and you have only such a direct transition, and it does not go to Fermi surface with other sign. And therefore, with such additional layer, it can work as a filter. So it can work. It is important for understanding of this sign change of the superconducting order parameter. And this is also, you see, could be important for making new devices, because based on such Josephson junction, you can essentially increase the frequency of this qubit communication. Okay, so I then finish with scientific case and just about other, and just to say a few words about our collaboration. Our collaboration mainly with Germany and with IFW, and we have very nice project, so-called Ukratop project, when we could send our student for scholarship, for half a year scholarship, and it was very effective in a sense. Of course, Germany, Germans and this institution helped us a lot after Russian invasion. Many our people were there, but actual scientific output from that project was quite good, and recent output is Nature. It's not only Nature, but it is the main Nature of this output when our students were involved in this real research. And this Nature is important in a sense also in context of for quantum computing, because another more maybe perspective way to overcome this decoherence problem is to go to find topological superconductivity, to find topological superconductor in which it is possible to realize so-called Majorana fermion or Majorana zero mode, which are locally locations they are distributed, and therefore they are very robust in a sense of this decoherence. And it is there were many suggestions about such materials, but all of them appear to be not true, maybe. But what they found now, it is so-called platinum bismuth material, which has topological surface state, and they are superconducting. They have found superconductivity there, and they have found how they are topological. And now it is important thing to understand how to make a device based on this. Now this Ukratop project is converted to this GUKUMAT, German-Ukrainian Center for Quantum Materials. We get many equipment also from Germans, like furnace for growing single crystals, right? And this is about that was this is magnetron sputtering system, which is also important for us, and all others. And finally, a few words about importance of the synchrotron or perspective of the synchrotron in Ukraine. This is our institute. Here is Kyiv Academic University here, and this is Institute of Metal Physics. Here is our superconductivity department. And what is interesting that some times ago, on the beginning of this century, or the end of the previous century, when we met with Isaias in Argentine, It was the plan here to build small synchrotron. And now we go back to this idea of this synchrotron and we go back to this idea and plan maybe to build synchrotron here. And as the first step, we start with beamline, Polish beamline, Ukrainian beamline at Polish synchrotron. So for you who are interested in such kind of research, you are invited to join. Thank you for your attention.
Thank you, Sasha. I would like to say that we have one synchrotron here in Brazil too. Yeah.
Yeah, I know.
Yeah, of course.
I know, but I never been there, as you know. I never been in Brazil, and especially it's Brazilian synchrotrons.
Yeah, maybe one day. Okay, now who has? First of all, would like to say that this meeting, these seminars are organized by the LAFMAT network. LAFMAT is a network of researchers working in condensed matter and material science. Every Saturday, we have one invited speaker talk for us. Thank you very much again, Alexander. Congratulations for your improvement in your career, director. Fantastic. Now we have some questions. I suppose Leandro will has a question for you. Leandro, with you.
Okay. I was not expecting to be the first one to, but okay, let me thank you for the very, very nice talk, and it was very pedagogical, and I think I could get most of it. So my question is, I was very interested about these junctions combining pignites and niobium. How you have you continued with this research line, and have you seen that it's really because from a technological point of view, it's kind of in general people use this aluminum as you mentioned for practical reasons, but also because every new material also introduces probably some its own noise, no fabrication with different things. Comes associated with some etching process, some deposit process, and everything comes with its own contribution to the coherence. So my question was whether this has been, for example, implemented in some qubit platform or something else. So this is one question. Of course, I recognize that it must be very hard to integrate with something else. So this is why I'm asking. And the second question is, you mentioned that this acts like a filter. So I imagine, well, my question would be, are there signatures of these kind of contributions from the electronic density, electronic structure in the IVs? So this is the second question. Thanks.
Electronic structure of, I didn't get the last question.
Yeah, so this picture that you're showing, in particular the Josephson effect or tunneling, I mean, must take into account carries. So how supercurrent is, how Cooper pairs go from one material to the other one. So in principle, you mentioned there are some. It's like a filtering effect. So this is what you say. So my question is whether you can see signatures of this in the transport experiments or in any experiment related, which is not, of course, RPES or this. It's complicated.
Yeah, of course. Here, so I start okay, I start from the last question. The first question, okay, the first question was about whether we continue this work and some development. Yeah, of course, we here are focused on fundamental research, and we do not have enough and far from enough power or equipment to do now investigations in millikelvin range. Yeah, we have helium liquefier, which is unique for almost unique in Ukraine. Maybe we have the best possibility to measure at liquid helium temperature, but we do not have liquefier. We do not have cryostats. Yeah, for refrigerators for millikelvins. And this work we did in collaboration with within some projects with NATO, Science for Peace programs, with other colleagues. They are not finished yet, but I do not feel that we could do here much. We have some experts in our groups, even from older time, from Kharkov. They still 30 years ago they still have the Josephson contacts and qubits. They didn't call it qubits then, but all these characteristics they measured and they experience in this sense. But of course now the technology and all these companies are so far ahead that it is difficult to compete. And for us, it is more interesting, of course, the physics, and this is just like byproduct. The ideas. I quite understand the problems of technological problems it could be, and and we have of course some ideas how to do it. Yeah, for example. I'm experimentalist, but in ARPAS, and I actually this experiment, the history of this experiment was that my friend Volodya Krasnov, who is professor at Stockholm University, and I know he is very experienced in Josephson junctions, and I just asked him whether he could confirm that it is S++ symmetry in superconductors, not S plus minus. And he said, "Oh, it is not so easy. Just send us some students, postdocs, and he will try. We will help. He will do." And this is Alexei Kalinyuk from us. He spent there 3 years to develop this technique just to make a junction between niobium and iron-based superconductor. Of course, he just not the whole year spent there, but it is their equipment and quite a large experience. Therefore, quite a large time. Therefore, I understand it is complicated. And of course, niobium, one of the things, niobium is a very good getter. Yeah, it absorbs easily everything. Niobium is not the best thing for this. And we have another solution is molybdenum rhenium, which is much more stable and more technological. Therefore, if we develop this direction, we would look for another material, not niobium. Maybe. But when you then ask about this physics, I would say, less about this. So it works in the following way. This is ARPAS experiment, of course, the Fermi surfaces. No, the Fermi these are modeled Fermi surfaces, but they are modeled based on ARPAS experiment. Yeah. So we know very well the distribution in momentum space. But for niobium we have very complicated Fermi surfaces, many Fermi surfaces. Therefore, if you integrate it, you have almost constant. And therefore, when electron tunnel from niobium to without copper, they tunnels both in this portion of the beta here. They tunnel here, and this is just tunneling. You have deconstructive interference, right? You have in total you have almost zero on the signal. But when you put this in between, you put such a filter, such a Fermi surface. When electron tunnel from niobium, they first tunnel to copper and then tunnel to iron-based superconductor. Therefore, they could tunnel only through momenta which where this Fermi surface exists. and they can't tunnel here, or it is tunneling is essentially reduced.
Okay.
So of course, the much better would be to have this is projected Fermi surface, and this is projected Fermi surface from the Fermi surface of this is Fermi surface of kappa, and this is one projected Fermi surface, and then projected for the film, and you have intensity also in center. It is just less than here, but if you have single crystalline surface, a single crystalline layer. Then it would be much more effective filter, of course. Therefore, it is interesting direction, I think, of combination of different layers, starting from understanding of their Fermi surfaces.
Perfect. Excellent. I understand now. Thanks a lot. Very interesting.
Thank you, Leandro, for your question. Thank you, Alexander. Now, Professor Stewart.
Alexander, many thanks for your talk. I found that very interesting. Thank you. Also, you must have struggled a little bit considering the conditions at the moment. To a certain extent, you answered my question already. I was going to ask about the Majorana fermions, considering Microsoft this week published a paper on their latest device. So to a certain extent, some of the problems with the hybrid devices are things like states in the gap, the quality of the interface, the measurements that you're doing. Could you say something about that in relation to the surfaces? Now, you introduced ARPES, but I don't think you mentioned, say, a topological. I mean, you mentioned the bismuth materials, some of which have this topological surface state. Could you say something about your measurements in terms of, details of a surface that might be useful for a hybrid device?
Yeah, I just wanted to return to the slide.
Yes, yeah.
And this is just our experimental data for when I measured my first impression about topological insulators when they just started to appear, and ARPA spectra appeared. That here is just a bubble, that is nothing real. But then really we saw that there is such a surface state here. It is surface state, okay, surface state. It's not something unusual, but surface state in normal crystals, they are very sensitive to the cleanest of the surface. Any dirt of the surface just kills the surface state. And it is actually how you usually in experiment could distinguish surface state from the bulk state. If you have some two-dimensional bulk state or it is surface state, you could just a bit contaminate the surface just to put it, and they completely disappear. And I was very impressed when this sample goes to fast entry with the vacuum 2 orders of to magnitude worse than in the measuring chamber. And then I wanted to put it back and to see that spectra almost disappear, but this surface state are still there. They even goes to the Fermi level. And then with time it goes back, and when some dirt evaporated from the sample surface, and therefore the surface states, they are extremely stable in this sense. It is one thing, but I can't comment on this Microsoft paper. I saw it, and it is just some old compound. I do not know. I have no experience about this compound, so I don't know. I just could understand, for example, this bismuth. Now I will turn quickly to the last slide. Somewhere here it was. No, sorry. Sorry for this.
That's okay.
Yeah, okay. I wanted to show this stuff. You see, this is a cartoon of representation what they observe, and this means that it is there is some bulk structure, and in the bulk it is well semi-metal, and there is some electronic structure. They are Dirac, but at the surface, the states which are superconducting, they have, which they call now Fermi arcs. I didn't like very much the Fermi arcs, which was before. This is about superconductors, high temperature superconductors. That was story. But here they are really Fermi arcs in a sense that the states are at one surface. They are here, at another surface they are here. It is different in the counterpart. And this means that these states are distributed in space. In real space, they are distributed. And therefore, I could imagine that they are very stable for any disturbance. So, but that's it. And I do not have experience about this material which Microsoft shows.
Yeah, it tends to be indium arsenide. It's a narrowband gap. So, yeah.
I saw it. Yeah, I saw it. It's interesting. Yeah, of course,
Yes.
maybe it's real. It should be.
Yeah, should be. Yeah. Alexander, thank you for your talk. Very interesting. Thank you.
Thank you.
Thank you, Stuart. Alexander, we have another questions. And now, Ximena. Ximena, are you here?
Yes, Professor. No, we don't have questions from our audience here in National University of Colombia. The people only said thank you for your talk and the interesting topic about this. Thank you so much.
Thank you.
Thank you. We have Gabriela. Gabriela?
Hello, hello,
Okay.
I'm here.
Good.
Thank you very much, Alexander, for your talk. It was very, very interesting. All these experiments and the comparison with calculations. I was sort of in the same direction as Stuart, because I was curious about the surface states. I don't understand if in the experiments, well, how you could get rid of them in the experiments, or if in the calculations you could also, if you were calculating the surface states, to compare them with. I couldn't see when you were showing these were the surface states in the in your slide.
In previous one, right? On I again back to this that slide. Yeah. Oops. It was
Far
somewhere
away.
here, or here. This one, you mean?
There, yes. Where do you say, because the calculation is done with surface 2, with surface states 2? I don't see them.
Actually, this example of the slab calculation in a sense that if you have some, I'm not doing this calculation, but I was told by these people who are doing how they do it. Yeah. So that this is slab calculation in a sense that if you have this now. When you have a number of layers, right? You have some states which some states are goes to continuum and they form these bands, three-dimensional bands. But some states are separated from the continuum, some bands. So these are this is bismuth selenium, and this is 5 layers. And for these five layers, this is slab in 5 layers, and these 5 layers they have 5 bands, and only one of these bands are separated, and therefore it is separation. So this is which mark shadowed in blue. It is they are close to each other. They with number of layers they appeared each new band appear, but they are close. But some bands they are in distant distance, in some distance in between these bulk states, and these are surface states. So and that surface states that they calculate in this slab calculation, they are similar to what we see in experiment. It is correct.
Right. And the experiment, can you show it to me?
In experiment, in experiment, it is here. You see. So in experiment, it is here, but here it's already mixed with the bulk state, because in experiment it is actually more or less three-dimensional compound. It is quasi two-dimensional, but these bands they are KZ dispersion. And if you have KZ dispersion, you have not one band, but you have for different KZ different bands, because you have the small escape depths of electron. Escape depths of electron is a few layers. And this a few layers, due to uncertainty principles, that means that you integrate in the reciprocal space. If you two layers, you integrate roughly in half of the Brillouin zone in reciprocal space in KZ. And therefore, it is here you see this white feature. It is they reproduce the bulk band, and thin feature they reproduce the surface band. Not always, because for some bands they also could be very two-dimensional even for the bulk. But I told that for normal compound experimental, if you want experimentally to distinguish between bulk and surface band, you should just contaminate a bit the surface, and then bulk states still exist, but surface state disappear.
Here, okay. Okay, but I guess in the calculation when you put something on top, perhaps we still have the surface state. I guess, I don't know.
Something on top? What do you mean something on top? I just understand that how they do slab calculations. They do bulk material and let's say remove some layers. And then if they remove this layer but remains this slab thick enough, if they have these two layers of the slab, they have two bands. The band is split. If they have just one layer, they have some band. And
yes,
if
you have the slab, but you
yeah.
can also put some other atom from some other stuff.
Contamination, you mean, no?
Contamination, yes. And then, I don't know.
This I don't know actually. No, I understand topological protection. For me, I understand in two ways. One way it is how I observe it, because what means that in experiment the bands disappear. This does not mean that it disappear that they should disappear from calculations. That means that they became so wide and so low intense that we can't see it, and they became white when the scattering increases. And just if you introduce some dirt on the surface, the scattering forward scattering just unitary scattering increases. It means that quasi-particles at this level just scatters, the lifetime reduces essentially, and you just could not see this band. But topological states, it not happens with topological state, because phase space where electron could scatter it much smaller, because there is different spins around the Fermi surface. If it's not topological, then all the states are degenerate in spin, and from each state it could scatter to another state at the Fermi level. But if it is topological, then at each other state you have different direction of the spin, so you have at least half of the states less, roughly, and therefore it is much stable. But from topological point of view, I understand that this band should be there anyway, of course, and that should be stable. But we just could not see them. It is just a different disappearance.
Right. Hey, thank you. Did you say anything about building a cyclotron in Argentina? I was not, I couldn't hear very well, but did you say something about Argentina?
I have no experience with synchrotron in Argentina, no.
Okay. No, perhaps it was something, I
No,
heard something.
I said that we met with Isaias in Argentina.
Okay.
The end of
Something wrong.
last century, in 1990. In
No, I
1990.
was too optimistic to think about a synchrotron in Argentina.
No.
No, it's not real. No, well, thank you very much for your talk.
Thank you.
Okay. Thank you, Gabriela. Thank you, Alexander. Edgardo, your time. Edgardo? No.
Hola, hola. ¿Me escuchan ahí?
Yeah.
Okay, fine. Alexander, very nice your talk. Very interesting your topic. I have a very, very basic question. Sorry, but it's very not easy, but very elementary to the question. How you choose the material to study? Because I understand the theory is quite not completed, so it's very difficult to find new material theoretically and then to take the sample and measure. And understood that the prepare to sample is quite expensive, time consuming. So how you choose the material, how would you choose the doping material to prepare the samples?
Yeah, of course, in theory, when you apply to some projects or to even to synchrotron, yeah, you usually should explain how you came to this material and how you should choose it. Yeah, but usually it is rather accidental in a sense that if you have some material and if you have some crystal growers. Which suggest you some new material and you have time, you could try it. And if you see something interesting, you go in this direction. Of course, because usually it is usually very hard if you want focus on some material and want this material to be synthesized and then measured. Of course, there are many different problems could appear. And for example, with ARPES, angular resolve emission spectroscopy, we should to have very clean and flat surface. And this means that this material should be cleavable, that they should be, we call it ARPESable, yeah? And cuprates appear to be very good because this is van der Waals also materials, they're very easy to cleave. Not all the cuprates, but for example, bisco cuprates. And this is actually why it is problematic for me to call our experiment smoking gun experiment, because it would be nice if we have bismuth superconductors and we have for them ARPES and neutron data. But the problem is that for neutron you should have bulk crystals, very massive, it's proportional to volume, and it was made for VBCO samples. It was most of the for LSCO and for VBCO samples, and VBCO samples are more difficult to cleave. LSCO is even harder to cleave, and when you try to cleave it, you have something like mountains, and it is you could not get good spectra from this sample. But for example, VBCO has different problem. When you cleave it, you have polar surface. You have at the surface you have just this copper oxygen chains which completely change the doping level of the surface comparing to the bulk. And for bisco is perfect for ARPES. You just could put a film, scotch tape, and you can remove it, and you have a very good crystal. Because what is important that at the top you have bismuth oxygen layer, and then strontium oxygen, and then only copper oxygen, and therefore the first copper oxygen layer is quite protected. So it is. I tell you all this detail just to illustrate that it is quite difficult from the beginning to plan which material to measure. But of course, if it is very interesting material, it already how many force, how much you can spend for this for preparation to this experiment, of course. Therefore, it is a very complicated question, and there is no simple answer. But I would say that most our results are similar to, for us, it's picking mushrooms. I don't know whether it's popular in Brazil to pick mushrooms in the forest, but in Ukraine it was popular, and And I could compare it with mushrooms because you just go somewhere and pick up samples which could be interesting. Maybe it's not now, but then you see, oh, it was interesting, and you could go back. And so this is many tries should be.
Okay. Thank you, Alexander. Congratulations for your talk. Very nice. Thank you.
Thank you, Edgardo. Alexander, thank you very much again for your very nice talk and clear. Now, if possible, open your camera, please. Hello? Oh, thanks. Okay, thank you. Ariel, sorry, sorry for forget you. We have more than one person to do a question. Ariel, your time. Sorry. Your microphone. You are mute.
No, sorry. Congratulations for your presentation. It was very good, but now I don't have any question. It was a very good presentation, and I think that it was clear. Thank you very much, Alexander.
Thank you.
Thank you. So, Luis, would you like to say anything?
Yes, thank you very much, Alexander, for your talk, for your accepting the invitation to give a talk for this network today. And I hope the peace comes to arise soon to Ukraine, and everybody will be happy. Thank you very much.
Thank you. It was my pleasure. Thank you very much for invitation.
Okay. So everybody, thanks again, Professor Sasha. And so it's finished our session. Sasha, keep in contact. Keep in contact. Okay. Please, everybody.
Bye-bye.
Bye.
Okay.
Ciao. Ciao, ciao. Bye.
Ciao.
Arigato.